we've introduced these partition functions without really talking about what their functional form is. So I want to take this opportunity now to evaluate a partition function so you can see how one might do it and also what it might depend upon. Now we're going to do this for the motion of molecules in a box. So I'm going to assume that our molecules are situated in a cubic box, which means that all three of the dimensions, Lx, Ly, and Lz, are equal to the same thing. They're equal to L. Now we learned earlier that the energy levels for translation, that is for motion within this box, can be written quite simply as Planck's constant squared divided by 8 times the mass times the length of the box squared. In this case it's the same length for all three dimensions. And then it's got a dependence on three different quantum numbers, nx, ny, and nz, where these quantum numbers, I'll just say nx, is 0, 1, 2, 3, and so forth, and the same is true for ny and nz. All right, so these are the translational energy quantum numbers, so we can use this now directly in our formula to calculate a partition function for translation for a given molecule. So using our standard formula, okay, we're going to do a summation over all of the states, but now I can actually enumerate those states by using these quantum numbers as labels. So nx would go from 0 to infinity, ny would go from 0 to infinity, and nz will go from 0 to infinity. And now my term in the sum is going to equal to this. I'm going to write out this exponent like this instead of like e to the, but it means the same thing. And I'm going to use beta instead of kt, so this is going to be equal to minus beta times these e trans, which is this expression here, so I'm just going to write it all out. H squared over 8ml squared times nx squared plus ny squared plus nz squared. But one thing I'm going to do to simplify this a little bit is you'll notice that the dependence on each of these quantum numbers is essentially the same. It's the same functional form. So if I were to actually write this out as three different summations, I would have e to the minus beta h squared over 8ml squared times n squared, or nx squared. I would have a very similar expression for ny, which would e to the minus beta h squared ny squared over 8ml squared, and a very similar expression for nz, e to the minus beta h squared nz squared over 8ml squared. But all three of these summations are going to give me the same answer because I'm summing over the same values of n, and I've got the same constants in here. So I can simplify this by simply writing this as one summation going from 0 to infinity of e to the minus beta h squared n squared over 8ml squared. And then, since it's the same answer for each of these three, I just cube that result. All right, so what I'm going to care about is evaluating this. Now I'm going to do two things to make this task a little bit easier. First, I'm going to define a constant so I don't have to keep writing all these things out. A constant that's equal to this set of constants. So now my partition function is simply going to be the sum from n equals 0 to infinity of e to the minus cn squared, evaluated over all those values. Oh, and I've got to cube that to get the partition function. All right, so that makes things simpler. But I also want to note that this summation is over discrete values of n, which means that it's kind of like adding a bunch of rectangles together to come up with an area underneath some curve. So if this is my curve, my exponential decay curve shown here, then these boxes are the summation here. But what if those boxes are really, really narrow? In other words, what if C is really small so that I've got a whole bunch of boxes here? Well, it will turn out that this sum can actually be very adequately approximated by an integral. Now you might say, oh my God, you've just made the problem much more difficult. But in fact, no, I've made it much simpler. And let me show you why this is. So if I take this sum from n equals 0 to infinity of e to the minus cn squared, and I say that this can actually be adequately approximated by an integral that looks like this. And instead of n, which is a discrete variable, it can only have integer values, I'm going to substitute that with x, which can take on any value. So you can see this is an approximation. But I know the answer to this integral. In fact, it's well tabulated, and that answer is pi over 4c. All right? You can look that up in an integral table, or you can plug it into Wolfram Alpha. It doesn't matter. This is what this integral will give you. So now if I substitute in my value for, for c, if I use this, I can get a more explicit expression. I can find that this integral, in fact, is going to give me something on the order of this. So I've got pi, I've got 4 in the bottom, and now I'm going to do the inverse, or the reciprocal of c, so I'm going to have 8ml squared in the numerator over beta h squared in the denominator. Okay, you notice the 8 and the 4 are going to cancel to give me a 2. And I'm going to take this beta and turn it into 1 over kt, so it's going to put kt up in the numerator. So the net result of doing this integral is going to be to give me 2 times pi times the mass times kbt, that's where the beta was, over h squared. Oh, and I forgot the L squared. Now the L squared, I'm going to bring it outside of this square root sign and just call it L, and you'll see why in just a minute. All right, so this is the value of this thing that's in parentheses, so it is that. So now if I want to write down the translational partition function, I need to cube it. So now when I write down z trans, I will end up with an expression. I'm going to use parentheses to indicate this a little bit more succinctly. kbt over h squared. That's just the stuff that was in the square root sign. A square root is the same as raising something to the power of 1/2, so when I cube it, I'm raising this to the power of 3/2. When I take L and cube it, what is that? Well, that's just the volume of the system. So in fact, I get this really nice compact form for the translational partition function of this molecule in the box, and in fact it's such a special form, I'm going to put a square around it, because this is our final result for the partition function for translation. Now, when you get a result like this, I want you to start thinking about things like this. I've got 3 parameters in here. I've got mass, I've got temperature, and I've got volume. So mass, temperature, and volume. Now, notice the mass and the temperature are in the numerator, raised to a positive power, and the volume is out here. So, in fact, when each of these increase, it has the same effect. It causes the translational partition function to increase. So that's useful to know. So it means that if I want to increase the availability of states to my system, I might just increase the volume, or I might increase the temperature. If I have a system that has heavier particles than another system, it will have more states available to it because mass is larger. All right? So this is the sort of reasoning that I want you to be able to take home from this. Now you might ask, what is a typical value for this translational partition function? In other words, how big is this in the greater scheme of things? Well, if I use a typical value for the mass of molecules, so it's about 10 to the minus 25 kilograms. I know that's not a lot of kilograms, but the number will come in handy. Use my standard values for the Boltzmann constant, Kb, and the Planck constant, H. And let's say I have a temperature of 300 Kelvin and a volume of about 1 centimeter cubed. How big will Z trans be? Well, it turns out that it will be on the order of about 10 to the 26th. In other words, 10 to the 26 states are available to a molecule that would find itself in this situation with a mass of about 10 to the minus 25 kilograms, a temperature of 300 Kelvin, and a volume of 1 cubic centimeter. All right, so you can see the translational partition function is actually quite large, and it's going to play a very important role when it comes to determining the properties of various molecular systems.